Hello, everyone. Welcome to Brain Blitz Audios. In this episode of Mind Maps, we'll be dealing with the chapter Amines. This is the 13th chapter in the chemistry syllabus of grade 12 CBSE. And as always, we'll be dealing with this chapter with the help of a mind map. Mind maps are pretty important and are an effective tool for last-minute preparations for exams. However, they can be pretty extensive like this one, and therefore this video is devoted to explaining this mind map in some detail. Now, as you can see, there are 7 stages of our video, and we'll be dealing with 7 important aspects of this chapter. Let's begin with the first part. So, what are amines? Amines constitute an important class of organic compounds derived by replacing one or more hydrogen atoms of ammonia molecule by alkyl or aryl groups. So these are basically derivatives of ammonia, which are obtained by the replacement of one, two, or all three hydrogen atoms. So in this chapter, we'll be first dealing with the structure and nomenclature of amines. Then we'll look at the preparation of amines, the physical properties of amines, the chemical reactions involving amines, diazonium salts, and the importance of diazonium salts in the synthesis of aromatic compounds. So that's the first part. So now we jump towards the second part that talks more about amines. So as you've seen earlier, amines are the derivatives of ammonia obtained by replacement of one, two, or all three hydrogen atoms by alkyl or aryl groups. So basically, it can be RNH2, R2NH, or R3N. All of these are amines. And according to the number of hydrogen atoms present, they're classified as primary, secondary, and tertiary. Primary amines contain one alkyl group and two hydrogen atoms attached to the nitrogen atom. And in secondary amines, two alkyl groups and one hydrogen atom are attached to the nitrogen atom. And in a tertiary amine, all of the substituents attached to the nitrogen atom are alkyl groups. So this basically is the structure of the amines that we're going to be discussing. And so in amines, this portion is nitrogen, and these are the substituents. One of them is, so here we're getting a tertiary amine, so it has 3 CH3s. So all of these are alkyl groups, so that mimics the structure R3N. So at the top, we have a lone pair of electrons, which is always present in nitrogen atom. And the other 3 electrons are attached and are associated with one atom from the hydrogen in the CH3. So all the alkyl groups share one electron with the nitrogen. So thereby it completes its octet. The angle between any two alkyl groups present in this combination is 108 degrees. So as we've seen earlier, the classification of amines are primary, secondary, or tertiary. So here ammonia, which is NH3, is converted into RNH2, that's primary, double R NH, that's secondary, and all sides R, that's tertiary. Let's look at the nomenclature of amines. To identify the common name, the aliphatic amines are named by prefixing the alkyl group to amine. So, for example, methylamine. So that would be CH3 NH2. In secondary and tertiary amines, prefix di or tri is put before the name of the alkyl group. So if we have CH3, CH3, NH, that would be dimethylamine. And if we had 3 CH3s, we would say it would be a trimethylamine. in the IUPAC naming system, that is, IUPAC stands for International Union for Pure and Applied Chemistry, there is the replacement of the letter E of the alkane by the word amine, and the suffix E of the arene is replaced by amine. So it will be methanamine. Methanamine represents CH3NH2, and benzene attached to an amine group would be referred to as benzenamine, or by its common name, aniline. So now let's look at the various methods of preparation of amines. So amines are prepared using 6 methods. The first method is the reduction of nitro compounds. So a nitro compound, which is also, so this particular one is known as nitrobenzene. So this is a nitro compound, and when it is reduced by passing hydrogen gas in the presence of a finely divided catalyst such as palladium, so it reduces to amine. So reduction takes place. So in reduction, the addition of hydrogen atoms takes place. So the oxygen is replaced by hydrogen. So the palladium catalyst is present in ethanol, and it also has hydrogen in it. So when the nitrobenzene is passed through this mixture, it forms amine. So this is aniline. This particular amine is known as aniline. So this is one way of reducing nitro compounds. The other way of reducing nitro compounds is by reduction with metals in acidic medium. So we have tin plus HCl forming an acidic medium and a metal, or we have iron, that's Fe plus HCl. HCl forms the acidic medium into which the iron metal is attached, is inserted. So over here, nitrobenzene changes to aniline. Now, the beauty of this reaction is that it can be reversible. So if you use iron in the presence of HCl, the compound that is formed is aniline plus FeCl2. Now, this can be easily converted back to HCl. So you only need a small amount of HCl, which can be reused over and over again. That is the first reaction. Let's move on to the second reaction, aminolysis of alkyl halides. So the carbon halogen bond is very easily breakable. So what we do is when we have an alkyl halide which contains this type of bond, the CX bond, and we react it in the presence of ammonia. So ammonia is reacted with an alkyl halide, and over here, this bond, the CX bond, is broken easily, and then we form a substituted ammonium salt. So this is an ammonium salt. Through this reaction, we can form primary amines, secondary amines, and tertiary amines, or we can form a quaternary ammonium salt. That is represented as R4N plus X minus. So the disadvantage of this reaction is that it yields a very mixture. So it yields a mixture of all these 4 products. So if we react it in any concentration, we might form different concentrations of primary, secondary, and tertiary amines along with quaternary ammonium salt. But if we have a large excess of ammonia, we can successfully create just primary amines. That is RNH2. So that's the second reaction, aminolysis of alkyl halides. Let's look at the third reaction, reduction of nitriles. Now, if you've learned in our previous videos, nitriles is the same thing as cyanides. So we have a nitrile here, and then it on reduction with the nickel catalyst forms the amine that's present here. And so this process is also known as catalytic hydrogenation. We have a catalyst and we use hydrogen and we hydrogenate it. And we also have other compounds such as NaHG, that is sodium amalgam, and C2H5, which is ethanol. So this is present in an ethanol mixture. Now there's another way of reduction of nitriles, and that is using LiAlH4, that is lithium aluminum hydride. Anyway, both these types of reactions will yield the same result. That is an amine. Now, the speciality of this amine is that this amine has one carbon extra than our nitrile. So if nitrile has one carbon, the amine would have two carbons. Let's look at the next reaction, the reduction of amides. Now, amides are represented by this formula. So we have an alkyl group, we have a C double bond O, and we have an NH2 present in one compound. And so to reduce an amide, we use lithium aluminum hydride, that's LiAlH4, in presence of H2O, to form amines. So this, again, is another amine. The next reaction is Gabriel phthalimide synthesis. So this complicated formula is for a phthalimide. So this type of substance is known as a phthalimide. So basically it's a benzene with two C double bond O's and an NH. So this is known as a phthalimide. Now, to get amines from phthalamides, we treat it with KOH. KOH is potassium hydroxide, and this is in the presence of C2H5, which is ethanol. So potassium hydroxide, which is present in ethanol, which is known as ethanolic potassium hydroxide, is used for the treatment of phthalimide to form the potassium salt of phthalimide. So this is basically a phthalimide, but instead of the H, you have a K. K stands for potassium. And then we heat it with an alkyl halide. So you have an alkyl halide, you have this potassium salt, and now you heat it, you get an alkyl phthalimide. So NR is now present. And then we use alkaline hydrolysis. So we use sodium hydroxide, which is an alkali, in the presence of water. So that is known as alkaline hydrolysis. So now this forms the sodium salt of phthalimide, and our primary product, this is known as a primary amine. So our goal is to get this amine, and the other byproduct is the sodium salt of the phthalimide. The final reaction is Hofmann bromamide degradation reaction. So we have an amide here, and now we degrade it using bromine in the presence of sodium hydroxide to form primary amines and some other byproducts. And so these are the ways in which we can prepare amines using other formulas such as amides. So you can use amides, we can use phthalamides to form amines, like so. Now let's look at the physical properties of amines. The first property is that lower aliphatic amines are gases. What is aliphatic? Now, aliphatic is the alkyl group which contains formulas such as CH3, C2H5, etc. So these are straight line compounds without rings. So there is no rings present. These are straight chain or branched. So formulas such as CH3NH2 and C2H5NH2, which are lower aliphatic amines, exist in the form of gases. So these are gaseous. Primary amines with 3 or more carbon atoms are liquid, and higher ones are solid. So C4H9 NH2, which is propanamine, exist in the liquid state. And as we go higher in the alkyl groups, we get solid amines. The next point is aryl amines are colorless but get colored on storage. So an example for an aryl amine is aniline, which is just benzene with an NH2 substituent. So this is usually colorless, but when you store it for a long time, they develop some color. Next point, lower aliphatic amines are soluble in water, while higher ones are insoluble. Now the reason for that is we have two H2s here. So this is a primary amine, while if we look at a tertiary amine, it's like this, the structure. So over here, we can basically form hydrogen bonds with other compounds. So we can, for instance, form a hydrogen bond with water. So it's basically a derivative of the van der Waals force. So we can form hydrogen bonds with water. So RNH2 is soluble, but R3N, which does not form hydrogen bonds, are insoluble in water. Primary and secondary amines form intermolecular association. So again, using the hydrogen bond technique present here, primary and also secondary amines, which contain a hydrogen or two hydrogens, can form intermolecular association, which is intermolecular hydrogen bonds. And using the same principle, we can conclude that primary amines have a higher boiling point due to the intermolecular association. Next comes secondary and tertiary amines have the least boiling point. Now, let's look at the chemical reactions which involve amines. The first reaction is to prove the basic character of amines. So amines are basic in nature. So to prove that, we react amines with acids to form salts. And an example reaction is RNH2, which is an amine, plus HX, which is an acid, forms RNH3X, which is a salt, an ammonium salt. So being basic, amines can react with other bases to regenerate their parent amines. So it's not the amines that regenerate. So what regenerates is the ammonium salt. So we have an ammonium salt here. So when it reacts with a base, it regenerates the parent amine. So if we have RNH3X, this is an ammonium salt, and we have OH, which is the hydroxy part of the base, that's the one that's more important. So when we react with these two, we get our parent amine, which is RNH2. Both are the same, plus water and the halogen atom. The order of stability of the ions in liquid phase is primary amines greater than secondary amines greater than tertiary amines. Now this is due to the intermolecular hydrogen bonding. However, if you're looking at the gaseous state, then tertiary is more stable than secondary, which is more stable than primary. The reason for that is alkyl groups are electron-giving groups. So when you look at a structure like this, the electrons here are transferred to the nitrogen, which makes it more stable. So when we have, say, R3N, this is actually more stable than RNH2. Now, the next reaction involves the acylation reaction. So here we have an amine, C2H5, NHC2H5. Now, this is a secondary amine for your information because it has two R groups and one H. So now this, which is known as N-ethyl ethanamine, it reacts with an amide. Again, an amide here is this one. This is our amine. So it reacts with CH3C double bond OCl in a basic medium such as pyridine. So we use the base pyridine in this reaction to form NN diethyl ethanamide and hydrochloric acid. So this huge compound here is referred to as NN diethyl ethanamide. Next, we move on to the carbylamines reaction. So what we have here, so we have an amine. It reacts with CHCl3, which is known as chloroform, and potassium hydroxide, that's KOH. So this mixture is heated to form RNC plus 3KCl plus 3H2O. H2O is water, KCl is potassium chloride. The term RNC is used for isocyanides. So for instance, if it was CH3NC, so if it was, say, CH3 NH2 that was participating in this carbylamines reaction, we would get CH3NC. This is methyl isocyanate, which is infamous for the Bhopal gas tragedy. Let's look at the next reaction. Reaction with nitrous acid. So amines, which are now classified into aliphatic and aromatic amines. So we have two reactions for the same acid. So RNH2, which represents an aliphatic amine, reacting with HNO2, this is nitrous acid, and it's formed using NaNO2 and HCl mixture. So when these two are mixed, we get freshly prepared HNO2. And we can only use freshly prepared HNO2 for this experiment, for this reaction. So now what we get as the product is aliphatic diazonium salt. So this here is known as a diazonium salt. We'll come back to those in a second. And these aliphatic diazonium salts are really unstable. So they dissociate in water to form alcohols, nitrogen, and HCl. The next kind of reaction with nitrous acid is with aromatic amines. So this is benzenamine C6H5NH2. So this is an aromatic amine. Again, it reacts with a mixture of NaNO2 and HCl that forms HNO2, and this reaction takes place between 273 to 278 degrees Kelvin. That would be 0 to 5 degrees Celsius, and it forms benzene diazonium salt plus NaCl plus 2H2O. Now, benzene diazonium salt is an important salt because this is further used in Sandmeyer's reaction to get more alcohols. So we get benzene diazonium salt and sodium chloride and water when we react aromatic amines with HNO2, that is nitrous acid. So let's look at the next kind of reaction. So this next reaction has a special name. So this is known as Hinsberg reaction. Now there's a reason for that. So we have this aromatic compound here, that is benzene, sulfur double bond O on both sides, and a Cl. So this is known as benzene sulfonyl chloride, which is also known as Hinsberg's reagent. So since there is Hinsberg reagent in the reaction, they call it the Hinsberg's reaction. So when this Hinsberg's reagent reacts with with amines, so this is a primary amine and not an aromatic amine because C2H5 is ethanol and not benzene. That was what I got mistaken. So it's actually a primary amine. So this is ethanamide, ethanamine, actually, ethanamine. NH2, so it's amine. This is ethane, so it's ethanamine. So we have Hinsberg reaction undergoing, which takes place between Hinsberg reagent and ethanamine. Now this forms N-ethyl benzene sulfonyl amide. So here we have an amide, and this amide is known as benzene sulfonyl amide plus HCl. Then we have some electrophilic substitution reactions. The first of these is bromination. So we have aniline, and so we add bromine to it in the presence of bromine water. So that's Br2/H2O to form 2, 4, or 6 tribromoaniline. So this is 2,4,6 tribromoaniline, which has the bromine in both ortho and para positions, because this amine substituent group is an ortho and para directing group. And another byproduct of this is bromic acid, hydrobromic acid. So that is represented as HBr. What happens in nitration? So the second reaction here is nitration, and that's where aniline is reacted with HNO2 in the presence, HNO3 in the presence of H2SO4. So that's nitric acid in the presence of H2SO4 at 15 degrees Celsius, that's 288 degrees Kelvin. So this reaction is known as nitration. So we combine an aniline with nitric acid in the presence of sulfuric acid at a specified temperature to form ortho, meta, or para nitroanilines. So nitro means NO2 is present. And we also have the various percentages. So para nitroaniline is 51%, meta nitroaniline is 47%, and ortho nitroaniline is just 2%. So these are the ortho, meta, and para derivatives of nitroaniline. The final reaction is sulfonation. So we have aniline here. It reacts with H2SO4 to form the anilinium hydrogen sulfate. That is this complex compound. So it's known as anilinium hydrogen sulfate. And again, when it's heated to 453 to 473 degrees Kelvin, it forms an acid. Okay, I seem to have reversed or have gone forward. So let's go back. And so we were talking about this acid, NH2, and attached to SO3H. Let's write the acid out. It's known as sulfonilic acid. And so it is the product of sulfonation reaction, which is an electrophilic substitution reaction. And on further reactions, we get a benzene molecule with an NH3 end and an SO3 plus end. So this is a special ion known as Zwitter ion. So it basically can react with both acids and bases. Now let's look at the next topic, which is diazonium salts. So diazonium salts have this general formula of RN2X, and the R is an aryl group. So it only works for compounds such as C6H5 N2X, because only aryl diazonium salts are stable. So if we have an aliphatic compound here, then it would not be stable. It would just dissociate into something else. So the R here is specific for aryl groups. And the X can be Cl, Br, HSO4, BF4, etc. So that can be any halogenized ion. So the ions include Cl minus, Br minus, HSO4 minus, BF4 minus, etc. So let's look at the preparation of diazonium salts. Diazonium salts are prepared by this reaction. So we have a benzene amine, so that's C6H5NH2. So diazonium salts are formed from amines. So this, in the presence of NaNO2 and HCl, this provides the HNO2 necessary. So the freshly prepared HNO2 reacting with benzylamine in the range of 0 to 5 degrees Celsius forms benzene, diazonium salt, and sodium chloride and 2H2O. So this is the primary method of formation of diazonium salts. Let's look at some physical properties. Now these diazonium salts are basically colorless and they are crystalline solids. So crystalline solids are a type of solids that we study in the first chapter. And these are soluble in water, but the special property here is that they are stable in cold environment, but they start reacting with water on heating. So when we heat benzene diazonium salt with water, then it starts reacting with water. Let's look at some chemical properties. The first property is Sandmeyer's reaction, and that's what we initially studied benzene diazonium salts for. So we have a diazonium salt here. So in the presence of cuprous halide and HCl, it forms benzyl chloride or aryl chloride and nitrogen. In the presence of cuprous bromide, in the presence of hydrobromic acid, it forms aryl bromides and nitrogen gas. And the same thing is true for cyanides, except that we use potassium cyanide instead of hydrogen. So let's look at the next reaction, which is the Gattermann's reaction. So in Sandmeyer's reaction, we used the chloride of the metal. However, in Gattermann's reaction, we use the direct metal itself. So basically copper with hydrochloric acid. So this system, we reacted with the diazonium salt to form an aryl chloride and nitrogen, but it also forms a cuprous halide. So if we reacted it with hydrochloric acid, we would get CuCl. And the same is true for hydrogen bromide. When we have copper with hydrogen bromide reacted with a diazonium salt, we get an aryl bromide and nitrogen along with CuBr. So let's look at the other reactions here. The second reaction here states that when a diazonium salt is replaced with an iodide ion, so Ki is potassium iodide, so it's K plus I minus, so the I minus is known as iodide, and that's the main reaction here. So the diazonium salt, it reacts with the iodide ion. So what they do is they remove this N2Cl part and they form a benzene iodide, so ARI. So it's an aryl group attached to an iodine, and then the other byproducts are potassium chloride and nitrogen gas. And this replacement reaction can also work with fluoride ions. However, we use HBF4 instead of substances like Ki or Kf. So this acid is known as fluoroboric acid, HBF4, fluoroboric acid. So diazonium salt reacts with fluoroboric acid to form an arene. So it forms an arene. It forms an arene diazonium fluoroborate. So BF4 is fluoroborate. So we form an arene diazonium fluoroborate, which on heating decomposes to form aryl fluoride, BF3, and NH2. The next is replacement by hydrogen ions. So we have diazonium salts reacting with hypophosphorus acid, that is H3PO2, and water to form aryl hydrides, nitrogen, and we have phosphorus acid, and HCl. The next reaction is aryl diazonium salts reacting with hydroxyl group. So basically it's replacement by the hydroxyl group. So it reacts with water to form AROH. So that's the aryl diazonium hydroxide salt. And then we form nitrogen and HCl. If this reaction is allowed to rise up to 283 kelvins, then the salt gets hydrogenized to this compound, which is known as phenols, which we studied in the chapter alcohols, phenols. So we studied alcohols, phenols, and ethers. So that was the chapter in which we studied this kind of compounds. The next reaction is the coupling reaction. So we have benzene diazonium chloride in the presence of a benzene atom with H and OH substituents in the presence of hydroxy group, so it's a basic reaction, to form an orange dye. So that is nitrobenzene. So this is a benzene with nitrogen that's double bonded to another nitrogen that is double bonded to another benzene, and it has a hydroxy substituent at the end. Then we have chloride ions and water as the byproduct. And so instead of OH, if we had NH2 in the end, we get a yellow dye. So the orange dye is known as para-hydroxyazobenzene, and the yellow dye is known as para-aminoazobenzene. And so we've come to the final part of this chapter, that's importance of diazonium salts in synthesis of aromatic compounds. So when we want to prepare substituted aromatic compounds, so substituted means, so this is the aromatic part, and we have something substituted such as Cl or say OH or say NH2, etc. So the diazonium salts are very good intermediaries. So these are used in many reactions that yield substituted aromatic compounds. Now when these substituted aromatic compounds are formed, usually we cannot prepare it by direct substitution to benzene. So what we do is we convert the benzene into the diazonium salt, and then the diazonium salt is converted into the substituted aromatic compounds. And that ends the chapter amines. So we've covered all 7 parts of it. So we discussed what are amines in general. We looked at their structure. We looked at the nomenclature. We went to the preparation of amines, the physical properties of amines, chemical reactions, diazonium salts, and the importance of diazonium salts in forming aromatic compounds. So that concludes the chapter amines. Did you know that the channel Brain Blitz Audios is known for its quality educational content? To be a part of our journey, please subscribe to our channel. If you like what you saw, please like the video and give us your suggestions in the comment section down below so that we'll be able to create more quality educational content. To get updates on our educational content, please click that notifications button. Until the next episode, see you soon. Bye-bye.